Hello, I'm Josh Starmer, and welcome to Human Stories in AI with StatQuest and Lightning AI. In this series, we'll hear about the career journeys of passionate AI experts. From their humble beginnings to conquered challenges, we'll be inspired by the real-world experiences of professionals thriving in the ever-evolving AI landscape. Human Stories in AI is brought to you by Lightning AI. Code together, prototype, train, and deploy AI web apps, all from your browser with zero setup. Personally, I love Lightning AI because it makes it super easy to use and learn from the StatQuest coding tutorials. Just go to the webpage, click on the Run button, and bam! You get code that you can play with without downloading anything or installing any packages. Today, we have special guest Fabio Urbina, an associate director at Collaborations Pharmaceuticals. Fabio combines computational tools and machine learning with classical small molecule, molecular, and cell biology techniques to address previously difficult to probe scientific problems. Specifically, Fabio finds solutions to drug discovery with machine learning. So, without further ado, Fabio, can you tell us about your journey to where you are right now at Collaborations Pharmaceuticals? How did this all start?
Okay, if we go as far back as possible. So my great grandfather, back, no, I'm kidding. I'm not going that far. No, it's a great question. So yeah, I guess as a kid, I was always really interested in science. It was something I was always wanted to do, something that I really enjoyed. I'm sure many people like me grew up watching nature documentaries and science documentaries and really enjoyed the process of learning. And so, since I was little, I essentially wanted to go do something in the sciences. Didn't know what that meant exactly as a kid. You really don't know what you're looking for, but something in that realm. And
Mm-hmm.
so, another sort of component to my, I guess, upbringing is that I was really into computers.
Okay.
I remember we got our first computer as one of the Apples, green text, Oregon Trail, and floppy disk. It was great. And so that sort of became one of my hobbies essentially on the side as I was going through school and whatnot. So in college, I decided to get a bachelor of science in biology and a minor in computer science. And so I sort of just dabbled in biology, and that's really where a lot of my interest lies. I remember taking my first cell biology class and thought it was like the coolest thing ever. And so sort of where I decided to keep my focus in that area. And um, yeah, so essentially, got a bachelor's of science in biology, and there's a really interesting internship program that I remember seeing on a door of one of our buildings, and it was to come up to Massachusetts General Hospital and do like a couple of years of lab tech research once I graduated in a lab that worked in a really rare disease called familial dysautonomia, which I'm sure most people have not heard of. Something like 400 people in the world have ever been affected by it. So it's a very, very rare disease. And so, not knowing what exactly I wanted to do once I graduated college, which I think a lot of people find themselves in that sort of interim what to do, I decided to go there and become a lab tech for a couple of years. And that's when I got really invested in essentially rare diseases and early stage drug discovery, which is what I focused on while in that lab. So we were essentially trying to find a drug of any sort that could potentially be a therapeutic for this rare disease, this familial dysautonomia. And so that experience made me realize that I really wanted to kind of dive headfirst into biology and really into the cell biology of things and really into the nitty gritty of what makes cells kind of tick. And that sounds a little bit quite different from my current area of research, but it'll come back around in a minute here. And so I joined a lab at UNC, Chapel Hill, which was the lab of Stephanie Gupton. And there I worked on neuron cell biology and neuron development. And essentially, how do neurons grow and make the connections they do in your brain from, individual blobs of cells to this very, very complex structure. And one thing I wanted to bring to that experience is some of my computational background. So throughout my time of working in biology, one thing I did was I always kind of weaved in some computer science or computation or statistical sort of analysis kind of grouped in to the actual experimental work. And so that sort of is what I did over the course of my PhD is applied computational image analysis to a lot of the cell biology imaging we were doing. So once I finished my PhD, I kind of realized I didn't really want to go into academia. It wasn't really what I was, that wasn't really the career trajectory that I wanted to go. So I wasn't quite sure what I wanted to do. So you'll hear there's a little bit of luck in this for sure when it comes to finding out, where you go in life. But I started looking for internships in industry positions. And so essentially started looking around for posts for internships that looked really interesting in biotech companies sort of in the area. And so good.
Was this while you were still a student, or is this after you'd gotten your PhD?
So this is while I was still a student. So this was
Okay.
about my last year. I knew I was going to graduate soon. Now, of course, my graduation schedule is a little messed up because I graduated in 2020, which is right when
Oh, sure.
COVID, yeah, and that sort of delayed a lot of things, and there was a lot of things that weren't quite sure there. Um, but yeah, essentially towards the last year of my PhD, you start thinking about what it is you want to do. And
Yeah.
usually the next step for a PhD, when you finish it, if you're going to stay in academia, is to go on and do a postdoc in another lab somewhere. And, I really like the area here in the Triangle area of North Carolina. Didn't want to move. I wanted to sort of jump more into my career stage rather than jump into the postdoc life and then sort of then go on to try to start a lab. So industry just seemed like the kind of thing I wanted to do. So yeah, during my last year of my PhD work, looked for internships, um, and you get permission from your PI to go and do an internship if you're going to do it in the middle of your PhD work. And so we worked that out, and yeah, I just happened to find this company, Collaborations Pharmaceuticals, which is where I ended up for the majority of my
Okay.
career thus far. And
Yeah.
they just had a lot of really interesting postings of what you could work on if you wanted to be an intern with them. So I essentially emailed Sean, who's the CEO, and he I think on a Thursday, I'll have to double check, but then he got back to me within an hour and was like, "Oh, can you start tomorrow?"
Oh, wow.
Very different experience than most.
Yeah. Wow.
Yeah, I will say there's a lot of one of the nice things about the sort of company I work at, I kind of try to push this perspective a little bit is as I think we have this sort of concept of what a biotech or drug discovery company looks like, and it's
Hmm.
usually from a very large pharmaceutical company point of view. And the pluses and minuses that come with that sort of industry viewpoint. But when I joined Collaborations as an intern, I think we had less than 10 people, including the CEO of the
Okay.
company. So it's very, very small. I almost want to call it a mom and pop operation because it's literally Sean and his wife are the ones who run it. And so,
Really?
yeah, so
That's cool.
it's very, very different. And I think that's what really drew me to it is just how different it was from the general sort of, drug discovery monoliths that I think of in my head. The other thing that really drew me to actually applying as an intern for them is that they focus specifically on rare and neglected diseases.
Oh,
So,
really? Wow.
so they actually forego the typical funding model of biotech where you go to get VC funding and raise capital and you have investors. Their actual original investment strategy was through grants from the government in order to create technologies and in order to find therapeutics for rare diseases, which are generally considered not profitable. And so that was a
Hmm.
real big sort of draw for me to them. So
Okay.
I really liked that they had such a very different model in that their focus was a lot more on the actual therapeutic side and wasn't completely driven by sort of like an investor type model, which
Yeah.
most pharmaceutical companies are. So yeah, so I started the internship and essentially just had a lot of random interesting problems thrown at me and tackled them, and it was a lot of new learning, I will say.
Mm-hmm. I bet.
Yeah, because it's so different from the biology that I studied. It was very drug discovery focused. It was very machine learning focused, and while I was fairly good with a statistical background, machine learning was fairly novel for me. So there was a
Okay.
lot of learning in that sort of first few months. Completed the internship, decided I really wanted to work there, so I, essentially applied afterwards, and they were happy to have me. And then I spent the next few months finishing my PhD, defending, and then joined the company essentially as a postdoc.
Okay.
And we could go through the whole process, but essentially over the next few years, I sort of rose through the company until I eventually became an associate director, mostly overseeing a lot of the machine learning, a lot of the software development, and sort of the creative, experimental, computational side of the company.
Can you tell us a little bit about what the machine learning, what you guys are doing, machine learning, what are you trying to accomplish with machine learning?
Yeah. So we focus on what's generally called early stage drug discovery. And so
Mm-hmm.
what that means is we may have a disease of some sort. So one of the ones, just to pick, is malaria, for example. And maybe we want to try to find new anti-malarials. And
Okay.
so what we do with the machine learning is, or I guess I'll start with the traditional drug discovery approach, is usually you would take a current anti-malarial compound or drug, and a medicinal chemist might take it and try to alter the structure of the molecule in order to try to find some maybe a better anti-malarial that's kind of similar. The sort of alternative is this naive strategy of you just kind of brute force it by getting a
Okay.
very large number of diverse compounds, and you create an assay that can tell you whether a compound has anti-malarial activity or not, and then you just brute force this whole entire set of compounds and try to find something randomly.
Okay.
And that's actually been a strategy that's been one of the more successful, which kind of tells you um, how non-specific and kind of random drug discovery is a little bit.
Yeah.
So
That's that's got to hurt the ego of the what did you say, structural
yeah, the
pharmacist
structural
or
medicinal chemist. Yeah,
yeah.
so finding new structures is a difficult problem.
Yeah.
And so machine learning is sort of this way to dive in and kind of bridge the two gaps there. And
Okay.
the way we use machine learning is we'll take our known drugs or compounds. So for example, we have a list of anti-malarials,
Okay.
as well as compounds that do not do anything to malaria. They're just sort of negatives. And
Yeah.
then we can give these structures to machine learning model and train the model to essentially take in a new drug chemical structure and decide or predict whether that new molecule is likely to have anti-malarial activity or not.
Okay.
And so then we can take this new machine learning model and we call it virtually screening. All we have to do is
Hmm.
take the structures virtually and essentially put them through this machine learning model and predict which of these, 1,000, 10,000, 100,000 virtual compounds might be anti-malarials. And then we can follow up the predictions by actually testing those compounds. And
Okay.
this way, instead of testing thousands and thousands of compounds kind of randomly, we can narrow it down to 10 or 100 compounds and test those. And that
Okay.
sort of accelerates our ability to find new drugs or new antimalarials in that case.
Off the top of your head, like of those 10 that you actually test, do all 10 show some efficacy or how accurate is this method?
Yeah, it's a great question. So we've had success rates where we've picked three compounds, and those three were all active. And
Oh
those are
wow.
actually three that we've taken forward. So that was a really, I think that was I forget exactly which viral we originally tested in, but I think it went on to become we found like three anti-Ebola, anti some sort of antivirals. But yeah, we've had success rates upwards of 3 out of 3 totally novel structures that
Oh wow.
ended up being efficacious. We've had something I think like another project we had something like 7 out of 10 were very efficacious.
Okay.
And then we have had projects where we tested 10 and 0 out of the 10 were actually efficacious. So we tend to have a very nice enrichment rate. meaning 10 to 100 or 1,000 fold better chance of finding new compounds, new drugs. But it is still a challenge once you build a machine learning model to decide, is this going to be applicable? Are we going to actually find what we are looking for? But yeah, we have had some pretty good success rates using these machine learning models.
Have you learned anything? When you get 0 out of 10 hits, has there been like, this disease has this characteristic that wasn't part of the original training data, or is there some indication as to why it didn't work?
Yeah, one of the things, and this is something we deal with, is we call it coverage or sort of an applicability domain, which is this idea of our training sets for these models are compounds and drugs themselves. But sometimes those drugs and compounds in the training set cover a very, very narrow chemical range. And all I mean by that is they all look very similar to each other structurally.
Yeah.
And so when we then build this machine learning model, it might look really, really nice on paper because what it's actually doing is just learning a very narrow chemical space. And then when we go on to predict on maybe something way outside the chemical space, the model is much more confident than it actually should be because it's only learned on such a narrow chemical space. So that's one challenge we generally face is how
Mm-hmm.
diverse is our training set.
Uh-huh.
And that tends to be the main problem in our field. Unlike text generation or image generation, is it's really really expensive to generate data sets. Usually you have to
Mm-hmm.
do full experiments on a single compound in order to get even one data point. So usually it's the sparseness of the data that ends up being the issue for the most part.
Which kind of leads to another question, which is usually when I think of machine learning, I think of big data, huge data sets. How large are the data sets that you're working with? I just assume that they must be much smaller because obtaining them is relatively expensive. You don't just suck down the entire Wikipedia and then work from that, or yeah. So, what can you tell us about that?
Yeah, I mean, you're 100% right. Our data sets are considered tiny by comparison to what you might
Okay.
think of as like, maybe what OpenAI is doing with ChatGPT. They're, like you said, consuming terabytes of data. We work on the order of hundreds of compounds or hundreds of data
Oh,
points, up to
okay.
maybe, I think the biggest data sets we get are generally about 100,000 data
Okay.
points. And so we are in kind of a small range, and
Yeah.
that does tend to present challenges that we've been investigating a lot of potential answers for, especially on the extreme end. We actually recently completed a project, which we're hopefully going to publish on soon, where our data set was actually 15 compounds in size.
Oh, wow. Holy
And we
smokes.
we managed to engineer a model that could actually give some predictive power and actually found some new compounds on a training set that's only 15 data points.
Now that is fascinating. That's almost like a nano data set, especially for machine learning. I think for traditional statistics, 15 is large, but for machine learning, that is the smallest data set that I've, other than like the really simple examples that I use in my little videos, which I intentionally make as small as possible just so we can see the math. But I didn't actually think it was possible to have a data set that small. I'm going to be honest, that just sounds like you're kind of blowing my mind.
Yeah, it's a field that doesn't get as much attention because it's, you don't get these massive impressive models, but few shot learning models or even zero shot learning models is kind of what these are generally called. And the idea is if you approach from the extreme end, how can you extract sort of a maximal information from these tiny data sets? And they're not going to be super impressive, but where you can focus their application and their predictions, they tend to be pretty accurate. So yeah, we were very excited to kind of get those results.
Can you share any of the tricks that you used? Can you tell us about the model one, the type of model that you trained, and share some tricks that you used to make it work with such a microscopically small data set?
Yeah, so the model type that we use, it's called a prototypical network. I'm sure most people haven't heard of it unless they've actually worked in this area. So
I've never heard of it.
yeah, so
Yeah.
it's a very, it's actually a fairly simplistic model underneath the hood, and it's
Okay.
designed that way on purpose because the simplistic models tend to have a lot of bias within them, which we generally think of as hurting modeling, but actually bias can actually be a good thing if the model's bias is sort of correctly aligned with what you think the data set structure is. So the simplest example of this is, for example, a linear model.
Hmm.
If anyone's done y equals mx plus b, that's the line and slope, that's a linear model. If your data set is actually linearly correlated, that model is most likely going to outperform just about any other model you could throw at a small data set because it's going to draw a straight line, which is your actual association. So that's, for example, a bias of a linearity within your data. Yeah, with the prototypical networks, the general bias is, we want to give it two classes of compounds. One that we know are, I'm going to stick to my malaria example, anti-malarials. One we know that are not. And so the thought is it's going to try to figure out what is the maximum difference between these two classes. What is so extremely different between these very small data points? And so we tried a couple of strategies. One of them being, can we choose negative compounds that look very, very dissimilar structurally from the positive compounds? Because when we have a data set of 15 compounds, we could essentially give it the entire data set. And sometimes if the structures are kind of on a spectrum where they all kind of look similar with ones and zeros, or sorry, with the anti-malarials and non-anti-malarials looking too structurally similar, that could be a difficult problem for the machine learning model to do. So we actually even pruned away some of the data a little bit to give it only the things in the negative that look as dissimilar as possible from the things in the positive, which was the anti-malarials. And that sounds almost a little bit like cheating with your data, but when you apply it to outside data, test set, finding new compounds, it tended to work really, really nicely in that fashion.
It's sort of like the ends justify the means. Like maybe it looks like you were cheating, but as a result, you had something that generalized a little better than it would have otherwise.
Yeah, absolutely.
I mean,
That's
that sounds good to me.
yeah.
That's yeah. And that's fantastic. And can you tell us a little bit about the type? I've already forgotten the type of model you're using. Can you tell us a little bit more about that type of model? I've never heard about it, so I'd like to kind of understand sort of how does it work?
Yeah. So the model type again is a prototypical network, which sounds kind of
Okay.
funky. Um,
Yeah.
and there's actually a second part of the model, which I won't get into too much detail because it gets a little too into the weeds.
Okay.
So the way our model is set up is it's composed of two pieces. One is what we call an embedding model, and the second is the actual prototypical network. So what the embedding model is trained to do is to take in a compound structure and generate a vector of numbers
Uh huh.
that represent that structure.
Yeah.
And the important thing that it's required to do when we train it is that structures that are similar to each other, so if you have two molecules that look really close to each other, the vector of numbers they produce should look very, very similar. So the
Okay.
numbers should align really, really well. Whereas structures that are very dissimilar should look very different. So if you
Okay.
lined up their numbered vectors, they should look different. They should have very different numbers. So this allows us to, we call it embedding our molecules into a vector space, which is to
Mm-hmm.
say we just numerically put these molecules in a high dimensional number space where structurally similar are numerically similar and the opposite.
Yeah.
So once that model is trained in order to do that, we take all of our molecules, we embed them into this vector space,
Mm-hmm.
and the prototypical network, the way it works, is it takes these number vectors, and it sounds so simple because it is. It takes the two classes, our antivirals and our non-antivirals, and it essentially finds the average of these vector numbers in this space,
Okay.
called a prototype. What you're doing is getting the average vector of the antivirals and an average vector. It's so simple, but it's so
Yep.
powerful when you apply it to small data. Once you have these sort of, they call prototypes, these mean vectors that represent the average antimalarial, non-antimalarial, then in order to predict a new compound as, maybe having antiviral activity, is you would put it through this embedding vector and you would find which prototype is your vector closest to. So is your new
Okay.
molecule closer to the zero class where there's no antiviral properties or to the antiviral vector or prototype?
Yep.
And
Yep.
it's very simple, but very, very powerful.
So it's almost like a nearest neighbor algorithm.
Yeah, I believe it's based off of K nearest neighbor actually is essentially the origin of that strategy.
So from my perspective, so I've got a. I hate to. I'm like tooting my own horn here, but I have a video on something called word embedding,
Hmm.
which is essentially what you described, but applied to molecules instead of words, and it does the same thing. And then you take those vectors of numbers that come out of the embedding network, and you basically apply k nearest neighbors to it to find and this to find sort of to then classify whatever your new molecule is. This sounds fantastic. I absolutely love it. I love the simplicity of it. I know right now when people think of AI and they think of ML, they think of ChatGPT and they think of these huge monolithic monsters. And these, from what I know, are incredibly expensive to run. They like just, they've got so many GPUs just chewing up electricity, generating heat, and need to be cooled down. Everything about them is expensive, expensive, expensive. And that's awesome and whatever, fine. But it sounds like what you've got is incredibly simple. And I'm going to guess that the hardware you run this model on is relatively modest compared to say what ChatGPT runs on.
That's understating it. I run these on like a 2015 Mac. Like there's not even GPUs involved in half of this. It actually is. Yeah, you hit a point there, which is something really nice. And I'm going to say our field, my field of drug discovery and machine learning, is the one plus side of these data sets being so small is that we can run them on pretty much any machine. So while we do have, fairly large GPU clusters for running deep learning models where we try to aggregate much larger pieces of information. When it comes to some of the smaller models, yeah, we tend to just be able to run these very simply locally on our own machines. Most people would be able to run these machine learning models themselves on their own, hardware desktop. You just need your modern day CPU and it'll work just fine.
I love it. I just love it. It's this to me. It's one of the unexpected things. Like for me, I just assume that everyone is, and maybe other people are like this too. But I just assume that everyone is doing something more fancy and more complicated than I could ever wrap my brain around. And this sounds, in a way, it's like, oh, I could do this. It's like and I know that I don't want to make it. I don't want to belittle what you're doing. I'm in a way, it's like I feel like I've been empowered by listening to what you've said. I felt like the crazy world out there isn't as crazy as I assumed it did. You kind of like brought it down and said, hey, get rid of all those silly extreme ideas that you have, and let me tell you what it's really like. And it's not so scary,
Yeah, I
and
completely
it's
agree with that.
reasonable.
I don't think it's belittling at all. I
Yeah,
think I think you're right.
yeah.
It's something that I wish more people would realize is you don't have to go and try to train your own transformer model with 96 layers in order to do machine learning or in order to even dabble and get something useful. A lot of it's no secret that a lot of fields still have a very small amount of data. The reason these image generation models and text generation models are so big is because they're essentially the only fields where you have a huge amount of data. And in any other application, it's I'll say it's actually a common thing for when someone kind of newish to machine learning comes into our field, that the first thing I want to do is the latest and greatest published model. And what's really funny is a lot of times, if you just train some of the simple old models, support vector machines that you may have heard of from decades ago,
Uh huh.
random forests even, they outperform some of the newer model types very easily actually in our field. And a lot of that has to do with, how much data there is and how each of the algorithms sort of treats the data. So it is a bit humbling because I did the same thing. I came into the field, I said, "Oh, this is what we're using. These are the features we're using. Random forest or vector machines. Oh, I could outdo this. Come on." And I started all these deep
Yeah,
learning
yeah.
models, and nope, I completely failed in my ability to outperform what was there. So that it was very humbling to come in and do that, and to really have to sit down and really engineer the problem a bit.
Well, hooray for the old models.
Yeah,
I'm a secret fan of all those old
excellent,
models.
excellent.
I love it. Well, to be honest, that's a cool. We could end on that if that's all we got. But if you do have any, final words of wisdom, anything for just a student or someone who's maybe changing their career, if you have any advice for them, we can just let me know what you got.
Okay. You might have to cut me off because I can talk forever. But yeah,
You're doing great. You're doing
I
great.
guess, the biggest thing I think I see people struggle with is thinking that they either don't know enough or they're really uncomfortable with, encountering a problem they can't understand right away. And, I've trained a number of students under me, and I think the biggest struggle is, yeah, you encounter something, you don't know what it is, and you shy away from it because it makes you feel bad because you don't like that uncomfortable feeling of not knowing, of not understanding. It makes you feel like maybe you're not smart enough to understand something. And that's such a small thing it sounds like, but I think that's actually one of the biggest sort of barriers to people kind of going on and being a lot more successful, I guess, or a lot more willing to plunge ahead into the unknown. And I say this only because I think I have something a little broken in my brain that I've never had that issue. Where if I don't know something,
Oh,
if I
really?
don't know something, I just don't know it. And if I try to understand it and I don't understand it, I don't understand it. But I'm going to keep trying until I eventually do. And so I don't think. I guess what I'm trying to say is it's the work you put into finally understanding it, not how long it takes you to understand it, that's really important. And most people who are in fields who understand and know a lot, I think most of them, they're not necessarily smarter than anyone else. I think they just are okay with realizing they don't understand it. They try to learn it, they still don't understand it. They try to learn it again, they still don't understand it. And they just keep going until they finally get it or know it enough that they can give it to somebody else to take over. But
Yeah, it
delegation.
sounds good.
But yeah, so I think getting comfortable with feeling really uncomfortable, it can be a really big boon to people, especially when they're thinking about changing fields. One of the difficulties I know, especially if you're coming from a very different background than what you're transferring into, is you're essentially starting over from scratch. You become an expert in your field over the course of, say, your PhD or even your undergrad. You feel like you become kind of an expert in the general area. And so you feel like you know a lot. And you've done this whole progress for 4+ years, 6.5 if you're doing a PhD sometimes. And you feel like you know a lot of stuff. And then as soon as you switch fields, you all of a sudden are almost starting from scratch. You don't know the lingo, you don't know the acronyms, you don't know what people generally do in the field, and that can be pretty jarring. And so that is also one of those pain points where as long as you're fine sort of going back and struggling through things again like you did at first, it won't take long before you eventually pick it up and are able to sort of run with it. And because it's not your first rodeo going down the research path, it tends to be a lot easier. It'll still take you a while, but it tends to not be too difficult. And so that's sort of what I found when I switched over from cell biology to sort of a drug discovery, machine learning. Well, yes, I had some experience in the past, felt like I was sort of reading the original papers in the field again. It was consuming so many reviews and so many papers where I didn't quite understand it, and then having to find go back into the literature and down more references, the rabbit holes, all that. But it's one of those things where I think if you can get past those feelings of almost inadequacy and can kind of push through it and recognize that you can learn it. You just have to put in the time and you just have to be comfortable with the uncomfortable. Then you can switch fields pretty much at any point in your career. I think it's scary, but if you have the capability of learning once a very specific set of, topics, you can do the same thing over and over again. There's nothing different about your brain from when you first started, except maybe, maybe you're a little bit older and takes a little bit longer, but there's nothing different about it from the first time you did it. So jumping fields can be scary, but it's 100% worth it if it's something you really, really think you want to do.
I love it. Well, on that note, thank you very much for being with us today, Fabio. It was great talking to you and hearing what you're doing. I learned a ton, which is why we're doing this podcast to begin with. So thanks again.
Thank you.